Good afternoon. Thanks everyone for sticking around. I guess today will be our last lecture. Before we start, I wanted to give some quick logistic updates about the final presentation and project report. So the presentations are going to be taking place next week over both lecture days. So please make sure to submit the presentations on Canvas before class begins. So the due date of the presentations for everyone, even if you're presenting on Wednesday, is going to be at noon on Monday, and so everyone has an equal amount of time to work. There only needs to be one submission per group. So don't worry about having every member submit a presentation. We only need one one set of slides for each group. So the presentation guidelines, try to aim for about a 10-minute talk. We have 7 groups presenting per class section next time. And so we want to be able to make sure that we can fit everyone in. That'll give us sort of enough buffer time, both for questions and also for sort of transitioning. And basically what I'll have everyone do is we will, I'll just let whoever wants to control it share their screen, and then we can do the presentations that way. Please make sure that everyone on the project has some opportunity to talk throughout the presentation. You should probably aim for, so my general rule of thumb is about 1 minute per slide. Okay, wait, I see a question coming in. Is there going to be feedback on the outlines? Yeah, so I will try and get feedback as soon as possible, I guess, because the presentations are coming up. I would say because it's sort of a tight turnaround between now and the presentations. You know, it's okay if not all of the feedback gets incorporated, but do make sure that that feedback gets incorporated for the final report. Okay, another question: any requirement on video stuff? Because the yeah, so I'm not going to make people, you know, present with video or anything. I know that not everyone has access to a webcam and so on and so forth. So hopefully you all have access to at least a microphone. If not, I guess, you know, we'll just roll with it, and you can be sort of exempt from talking. But I would prefer everyone get a chance to speak during the presentation. Okay, and so out of the 10 slides, you know, this is pretty sort of straightforward stuff. You know, giving a problem statement, background, methods, results, conclusions. So that's kind of a general framework, but it doesn't have to be exactly like this. Just that if you need a little bit of guideline to design the slides, we can do it. You can sort of look structure the slides as follows. Yeah. So I see a question: should our final report have the same outline, problem statement, background, methods? Yeah, exactly. And I'll actually post a final report guidelines. That's basically outlining what you're saying, and Yeah, and so the structure of the report should be pretty similar to the presentations. Okay, so the presentation order chosen in a random number generator. On Monday, we'll have the first 7 groups, and then on Wednesday, the next 7. Hopefully I got it all right. I know that also the group topics may have like shifted a little bit in emphasis. I'm just putting the original names. And I think I've updated the name, all the names in each of the groups. But if there's a slight error, hopefully you know which group you belong to. But this is going to be our presentation order for next week. So please make sure to attend so that you'll be able to present your project. Okay, and then the final report is going to be due on June 8th. So that's going to be the Monday after next. So you'll have one additional week after the presentation is turned in. And as I mentioned, I'm going to actually post a guideline for the final report later today on Canvas. For this one, you only need 1 submission per group. But then there's also going to be a project peer assessment. And this will require every person submit a peer assessment report. Okay, so it's not 1 per group, it's 1 for every member. And I'm gonna have a template which I will also post to Canvas, and I will make an announcement on Canvas as well. Okay. Lastly, well, actually, before I go on ahead, are there any other questions about the final presentation or the final report? Okay, no questions. So last thing I'll say before we jump into our lecture for today. Yeah, so if you guys could fill out course evaluations, that would be very much appreciated. Yeah, really sort of looking forward to hearing feedback from you guys about how this particular course can be improved, both for teaching style and in terms of the material. I know that this quarter is especially unusual, but since I'm sort of taking over this course from a longtime instructor, yeah, any tips or feedback would be very much appreciated to help out with improving this course for your future peers. Okay, so for our last lecture today, we're going to talk about the future of energy, and not just about sort of how other researchers and experts have thought about future of energy, but how you go about actually constructing ways to think about what different scenarios of the future may look like with regards to both energy and emissions and impacts on things like climate change. Okay, so can we meet the challenges related to energy and sort of on a very closely related topic with emissions and climate change and those associated impacts? And so we have issues with growing demand, right? And so development, economic growth, equity, So all of these issues are leading to ways in which we have to figure out how to deal with the future of our energy demand, whether it's making it available for everyone, and so that's sort of addressing the equity sense, how we can make sure that we're doing it in a way that's still leading to a strong and robust economy, and then also thinking about future developments in growing populations, and how you need to be able to meet those requirements, both for larger number of people and for greater access, especially in developing countries. We also think about and have talked about energy supply security, right? And so this pertains to resource availability. And so how long do we have before we essentially use up a particular resource? And how do we transition in order to maintain resource availability? We think about, sort of on a related concept, peak oil. And if you guys recall from that lecture, as we reach peak oil, the sort of future development and extraction of that resource becomes increasingly difficult. And at that point, supply will be hard pressed to meet demand. And so you are forced to think about other energy sources to be able to service whatever demand that you're getting from resources like oil. And lastly, environment and health. So when we talk about pollution, right, it's not just greenhouse gases. There are also local pollutants that affect air quality, and those health damages associated with that, increasing morbidity and mortality. Those in and of themselves are serious damages to consider when it comes to using certain types of energy. And then we also have greenhouse gas emissions, which are affecting climate change, which I think that I don't need to emphasize to you guys is a pretty big deal, right? Okay, and paths to a sustainable energy system. So this is, I think, really putting everything together. I think we've delved into the details of specific sort of energy technologies and pathways, and then thinking about how public policy, regulation, and legislation has sort of leveraged a bunch of different mechanisms to push these things forward. But sort of taking a step back, there's essentially two really sort of fundamental ways we go about this, right? So there are technical possibilities, and so that is things like new technologies or improving existing technologies to deal with a lot of these issues. So air pollution, climate change, access and reliable energy supply. And we have covered, I think, a whole slew of technologies, some of which, right, are ready for the market. Some might still be in the lab and getting developed, or would be really difficult to deploy at a large scale. And so the other sort of big topic that we've covered is with policy options. And a lot of the ways in which we are able to make a path towards sustainable energy is to trend towards stronger regulation of pollutants and of carbon. And so these may include things like securing supply of oil, energy efficiency standard, increasing renewable use worldwide. And hopefully you have in your mind a number of policies that we've talked about that sort of relate to these specific policy examples. And again, we've gone through quite a lot of stuff, and so it can be easy to get sort of lost in the weeds a little bit. And so I want to sort of pull us back out and think about this holistically. So how fast can our energy system evolve? So what kind of factors do we need to think about for a changing energy system? So first, energy prices can change really rapidly. So this is a history of oil prices dating all the way back to the mid 1800s. And we can see oil prices fluctuating, so this is all in 2014 dollars, right? And so it's taken into account inflation. And what you can see here is that in the span of just a couple years, you're talking about changes in oil price going from 20 up to above $100 per barrel, which is a 5x increase. And so that leads to really fluid, rapid changes in energy prices that can have sort of long-lasting effects in your energy system. So sort of on the next scale, we can think about how policy changes human behavior and energy use. And the example that I'm giving here is with the CAFE standards. Right at the instantiation of the standards here, we're going on somewhere between 10 to 15 miles per gallon up to about 25 mpg in the span of just 10 years. So you're talking about approximately doubling fuel efficiency in just a decade. So changing the primary energy supply, however, so going even to a longer scale can take decades. And so here we can see this is kind of traditional biofuel. So this is really using like wood for burning. We can see how primary energy has shifted in share back from the mid 1800s all the way to today and onwards into the future. How long is it going to take for us to shift away from a particular primary energy supply? And we can see from the trends here that those patterns tend to take place over the course of several decades. Okay, and so the other thing that I would sort of note about this particular chart is that a lot of the transitions going from left to right is associated with a shift from really high carbon fuels to lower carbon fuels. And kind of in hindsight, the transition looks quite smooth. And maybe you might think it's inevitable, right? We have this pattern of growth. But while we're sort of in the middle of the process, it looks anything but that, right? So a lot of these incumbent technologies are kind of reinventing themselves to compete with all the new incoming technologies. And so there is kind of a constant struggle and a very sort of competitive environment that is facing, the growth of this new stuff. Okay, so Energy prices can change quickly, but it can take decades to change our energy system. If you think back to lectures about specific technologies, the supply systems themselves can last a really long time, several decades to a century. And when we think about the actual devices and technologies themselves that use the energy, things like cars and home heating systems can last 10, even up to 20 years in some cases. And that presents a really, really big challenge, right? If we want to talk about getting to like a zero emissions vehicle fleet by 2040, 2045, sort of in line with a lot of California's targets, then you need to essentially start selling all of these vehicles, all sort of zero emission vehicles tomorrow, right? Because the big dirty truck that I buy today in 2020 there may still be a small number of them sort of driving around on the road 20 years from now. And so the fact that a lot of these systems and technologies last many years and are durable makes it an even bigger challenge for us to meet a target, even if it's a couple of decades down the line. Policy process can take a long time. I think it's no secret that legislature and regulators can be a little bit slow. They're not as nimble as like a startup company, for example, and it takes time for science to translate into policy. And so it's really important as we identify these critical issues related to energy, related to climate, that we push that forward into policy as quickly as possible so that can translate into real change in the real world. Global climate change is a problem with a century-long time scale. And so all of these transitions and changes that are necessary, they can be particularly difficult to kind of keep up the pace, and also maintain longevity against an impact that can be longer than the lifetime of champions of particular like climate change actions. And so it's not an easy problem, but I think if you look around at how things are changing today, I think we are on the right track. Whether or not we are going fast enough, that's maybe a separate issue. But hopefully, as long as folks like you guys are educated about this thing, we can continue momentum forward for supporting energy transitions, sustainable energy transitions. So what lies ahead for our energy future? From a supply perspective, there are a couple of different potential futures that we could see, right? We can have business as usual, where governments don't really do anything, and then you continue using fossil fuels, and then as those resources diminish, then you just transition to unconventional fossil fuels. We could stay with our current fossil fuel system and try to reduce environmental impacts by doing things like carbon sequestration. But we could also transition to energy systems that are more renewable intensive or even more nuclear intensive. From a demand side, there's also a really huge variety of possible futures, depending on whether you have, high to low economic growth, high to low energy consumption, and that's really speaking to kind of the overall individual demand of energy services. So, do people start to drive more or less, as a result of changes in social structure. And then changes in demand that are informed by technology could lead to a variety of energy efficiency outcomes. And so this would be affecting your energy consumption, because even if you do the same pattern of consumption, if everything you're doing is more energy efficient, that's actually going to decrease your overall energy consumption. Okay, so there are lots and lots of different factors to consider in the future of energy, right? A lot of the things that I've sort of just discussed, but there are a lot of these sort of fancy diagrams that point out all of these different factors and relationships. So how do we go about considering and evaluating potential future energy alternatives? So in some cases, it's pretty straightforward. So doing maybe like a economic analysis of like a coal-fired power plant compared to a wind plant in the same region. And so this is something that you guys could do, right? So we've done some examples about if I wanted to do like an economic comparison, you could do the LCOE calculations, and that would be one way to look at this. But in other cases, it can get really, really complex, right? If you're talking about more systems modeling, and if you are trying to look at, for example, like a larger scale policy, like what happens if I were to implement a carbon tax on the entire economy? And so evaluating those types of scenarios and policy outcomes definitely gets more difficult. And so we're not actually going to get into the details of how you would go about putting this sort of modeling system together, but we will talk about at a higher level sort of what considerations we make for including in any sort of systems modeling analysis. So some of the metrics that you might want to think about, so costs, so especially if you're thinking about economics. So there are things like the direct economic costs, and so this would be similar to what you guys were doing for the LCOE, for example. But we could also include social costs or externalities, and so it might be folding in something like a carbon tax or a carbon price into some of that economic analysis. We can think about emissions outcomes. So thinking about both greenhouse gases and air pollutants, and those can even be translated directly into impacts. So for greenhouse gases, you might think about like monetary damages from climate change, or from air pollutants, you might think of translating that into morbidity or mortality outcomes from increased respiratory disease. And then a couple other metrics for comparing. We can look at the resource base, consider energy security and reliability, which is a topic we spent a fair bit of time on this quarter. And then also thinking about social factors such as equity, which is rapidly becoming a really big topic these days, especially in California, where a lot of the climate change policies have now folded in considerations of equity and how, as we transition to sustainable energy technologies, how is that affecting, disadvantaged communities compared to other communities in California. And so, a lot of the climate change goals affect everyone, but the way in which you do the transitions could disproportionately affect communities in different ways. And so that's important to keep in mind. So some of the analytical tools for understanding energy futures. There is engineering and microeconomic models. You've got top-down energy and economic models and bottom-up energy and economic models. Again, we won't go hugely into a lot of the details here, but we will mention a little bit of what these are. There's integrated assessment models, which I believe I've touched on in this course, where we're thinking about the integration of the energy system across many other sectors. So thinking about economy and environment. And then all of these, this probably shouldn't be, it's a bullet point on the sort of same level. All these different models can look at different scenarios, which are important to understand both what the futures looks like, but also to give some understanding, like if I were to enforce a specific policy or regulation or legislation, I could, before you put that policy into place, understand some of its impacts by looking at scenarios coming out of these models. So engineering and economic models, these are performance and cost models of energy systems. Specifically, you often look at components individually and sort of put them together. When we think about uncertainties and sensitivities of specific outcomes, these things can be pretty readily modeled. We typically do these for specific regions or specific markets. And you're able to get into sort of finer detail because you're working on a sort of more digestible or tractable sort of scale. So to look at the end state of transition, we often do this thing called point estimates, which are based on projections of technology and fuel prices in a particular year. And essentially what happens is, say, electric vehicles get more price competitive than gas vehicles at a certain year, because what we're doing is like we're decreasing the cost over time. And once it hits a certain threshold, then that new fuel or technology suddenly becomes competitive, and a lot of people will start to adopt it. Or the other way is with time evolving performance and cost projections or learning curves. So this is where over time costs are coming down, or you assume adoption goes in a certain rate. And you can couple that, to example, with infrastructure. So a lot of this is based on sort of rational engineering and economic rationale. And most of these are often a lot of these bottom-up models that I was mentioning. Yeah, and on the demand side, we can use a lot of economic theory. to look at how consumers will respond to different options, or how people in general might respond to a particular policy, especially ones that affect market conditions, such as carbon taxes and cap and trade. For integrated assessment models, these are models that link the energy system, the economy, and atmospheric chemistry, so that you're getting the suite of the engineering and economic side alongside the actual sort of physical impacts that we observe in the real world. So these oftentimes have these top-down rates of changes for adoption of new technologies, whereas bottom-up models will build up energy use and emissions by looking at individual technologies. Infrastructure changes in these sorts of models are usually kind of like a time delay in implementing new technology once it becomes competitive. And then rational and geographic concerns. Because integrated assessment models operate usually at much larger scale, so you're talking about multiple countries or worldwide, specific issues related to a particular region or a particular geography can be kind of worked at in a sort of in a backward sense. In a bottom-up model, you'll oftentimes have these already, but in a top-down model, these kind of concerns are elicited out from the modeling. You don't often get high resolution by region and by time, because these models are so complex and they don't go into like individual nuances of a particular, country or state. Okay, and so all of that is basically to give you guys, again, a high-level view of how a lot of experts are going about modeling future of energy. And then we sort of distinguish, I think so far I've been conflating these two words a lot, but there is a sort of a distinction between how we choose to look at the future. And so one is called a forecast, where we are trying to predict the future based on the best sort of information. A lot of these forecasts are short-term in nature, but not always. You can have long-term ones. But you can think about this like a weather forecast, right? And so they give information on what you think is going to happen. Scenarios are a little bit different, right? These are images of a future or alternative futures. They're not quite like a prediction or forecast. It is one particular way in which the future might unfold. And these are particularly useful when we're thinking about energy policy, because with a forecast, I'm thinking about today, sort of business as usual with all the sort of transitions that we have going on right now, like what is a particular, energy future going to look like 10 years from now. In scenarios, you might be more flexible and say, hey, what happens if I implement this policy or this policy? And I can look at a suite of different alternatives to help provide guidance for how to move towards a particular target. So with forecasts, you're thinking about what is likely. With scenarios, you're thinking about what could be. in the approach for forecasts, it's thinking a lot about rationally looking at specific outcomes. Whereas with scenarios, it's almost like a different train of thought where you are really more focused on process and strategy and learning and how to not necessarily say, oh, the most optimal sort of economic pathway, but how can we get to a particular topic? One of the distinctions between the forecasts and scenarios is that in a forecast, you're trying to look at characterizing uncertainty and trying to figure out the most likely pathway to a particular most probable future. Whereas in a scenario, by exploring lots of pathways, you're essentially exploring the uncertainty itself. For methods, a lot of the techniques and analysis ends up being similar, but the way in which they're employed can be very different. And so with forecasts, oftentimes it's a continuation of existing trends, whereas scenarios, you are evaluating a lot of like qualitative changes that could happen in your system. Okay, so I'll probably tie up this slide and say that in terms of actors, I think that kind of on both sides of the aisle, you have folks who are interested in forecasts and scenarios. And I think I don't want to paint one in particular as being better or superior. Having a good grasp of forecasts gives you, for example, a clear view of where we're headed. And having a good grasp of the scenarios gives you a nice handle on what we could do to change the future, or given a particular action, how is that going to change the system in a particular way. So when we build a scenario, so of the latter of those two things, we choose a question and a time frame. We identify key factors about the future, collect data, and then we think about changes in technologies, changes in the economy, and changes in policy. And in each of these sort of things, we are developing sort of storylines and trends and transitions. And we use a rational sort of modeling framework to help evaluate the qualitative sort of alterations that we've made to the economy, policy and technology. So to give a nice sort of high level example of all of this is from the IPCC's special report emission scenarios. So this is where a team of experts identified sort of two of the most uncertain factors leading to potential changes in our energy system and the associated emissions. And so this is for policy. Do we lean more towards being sort of economically efficient and sort of rational, or do we think about trying to integrate in environmental externalities and thinking about impacts of emissions and other environmental changes, ocean acidification and so on. And then the other uncertain factor is political organization. Are we, as a human species, are we going to start to think more globally and more as for sort of humanity in general, or are we going to be more regional and be sort of more locally patriotic or nationalistic? And so this is a nice little chart here that divides these into these two axes. So you've got your sort of economic and environmental axes sort of on your vertical, and then global and regional on the horizontal. And so A1 is like if you are more economically oriented and more global. B1 is if you are global and environmental. A2 is if you are more economic and regional, and B2 is if you are more regional and environmental. And the thing that sort of informs this tree are all these changes in your population, economy, technology, energy, and so on and so forth. So if we start more in the top right, so A2, the sort of scenario that is being described here, these experts put together these sort of generalizations where it's a lot more self-reliance, preservation of local identities. You have a pretty high population growth. Most economic development is oriented to benefit your local regions. And technological change ends up being sort of fragmented and slow. As we move sort of clockwise in B2, if you're regional but more environmental, then you pursue more local solutions to environmental sustainability. Population growth is a little bit more moderate, and you get intermediate levels of economic development and technological change. Sort of jumping across to A1 in the top left. So this is where your economic and global. So here you have really rapid economic growth, low population growth, and a pretty fast introduction of new and more efficient technologies. And then finally, in B1, you have low population growth, rapid changes towards service and information economies, reduced material intensity, cleaner technology, and more global solutions oriented to environmental sustainability. And these qualitative outcomes that the experts put together were able to quantitatively measure through existing models that IPCC used to understand impacts. And so here we can see the temperature changes associated with particular outcomes. So if you are A1, A2, B1, B2, and you can see that the sort of environmentally oriented scenarios for B1 and B2 lead to lower impacts on climate change. Yeah, and so again, we're not really getting into the nitty-gritty stuff about how you sort of model this. Just sort of pointing out that there is this way in which we are thinking closely about qualitative differences and scenarios for a variety of different outcomes, and we are able to model and measure those impacts of particular qualitative scenarios. Okay, so there's also a set of scenarios that Shell, the oil company, ironically, kind of put together to also think about this, where you have this two different set of axes, strength of leadership and mechanisms to share common interests. And they call this sort of the if you have a lot of good leadership and you have ways to share common interest, you can get below a 2-degree change, and they call this the shell sky scenarios. And to give a sort of high level picture of what they've sort of modeled is this transition away from oil to renewables, which, you know, I think it speaks a lot to you know, maybe not necessarily Shell being a good company, but the fact that one of the largest oil companies in the world is thinking about a sort of complete pivot from their existing business model, right? Away from oil to a different sort of energy resource. It speaks to the fact that a lot of companies can sort of see the writing on the wall for things like climate change. And so this particular set of trajectories, or the sky scenario that they're looking at, is a actually very sort of comprehensive modeling effort for how we can transition away from fossil fuels to sustainable energy resources. And this chart gives you a sense of some of the technologies and investments required across this sort of timeline. And they actually do a fair bit of quantitative analysis to look at some of the numbers here. And so here is an example of what they're showing in terms of current day use of energy resources from their own company perspective. And so looking at the net emissions from fossil fuels and then what they're doing for bioenergy production and use, and thinking about how they're going to transition away from that by 2050. So here you can see in 2020 you're at 35 gigatons annually, whereas here you're getting down to about half of that. I think that this particular targets a lot of climate change activists may and regulators and legislators even may see this as kind of not enough, because you really, particularly in places like California or the EU, where there are targets to reduce your emissions much more drastically. Nevertheless, I think that the company has outlined a sort of real method in which they would go about trying to get to these particular outcomes that they're showing in their sky scenarios. Okay, why don't we take a break here for 5 minutes. We'll pick up again at 1:09. I don't have too many slides left, so we're most likely going to end a little bit early today. But since we're an hour in, let's take a quick mental break. I see a question here, slides 29 and 30. Is that global data or US data? I believe that's global data. And actually looking at the numbers, this is probably not just Shell. I think this is all fossil fuels. Because generally you're around 30 to 40 gigatons of CO2 um, of global CO2 per year. Yeah, so this is definitely global. Okay. And with that, let's continue onwards. We're basically going to close out today with an example of developing a scenario. It's or a set of scenarios. It's not so complicated to do that, and I think the scenario itself is pretty straightforward. But the framework and logic of the development of this scenario is really sort of the key takeaway, rather than thinking specifically about a particular equation, right? Again, we've talked about, we're sort of repeating the slide from before, right? Developing a scenario. And so what do we want to look at here? Let's evaluate scenarios for reducing US oil use in cars. So oil use for cars in 2010 is 8 million barrels per day. The average fuel economy is 20 miles per gallon in 2010. Number of cars grows by 2% per year between 2010 and 2040. Number of miles traveled per vehicle, in other words, the VMT, stays constant between 2010 and 2040, and cars last 10 years. So this is a pretty common type of thing that you go about doing. And it's something that you end up, I think, getting more and more comfortable with doing. I was trying to introduce this a little bit to you guys when we work on the homework, or even on the midterm. You know, oftentimes, especially when you're in school, you kind of expect you kind of expect that you know, you're given some equation, and the parameters in the equation are kind of given to you, right? And those are the assumptions that whoever wrote the homework or test are making. But at a certain point, you need to start making your own assumptions and understanding sort of what's reasonable and whatnot. And so a lot actually of, you know, writing scientific papers and publishing in journals is building off of assumptions that either you make, or assumptions, building off assumptions that other people make, and you sort of figure out good ways in which to justify certain assumptions. And so these are the ones for this particular example. They're pretty simple assumptions. And straightforward to get. And the reason we make these particular assumptions is because this is the sort of data that's necessary in order for us to calculate the implications of the different scenarios. So the three things that we're going to look at is three different scenarios: a low efficiency scenario, where we're going to call this the sort of no cafe policy, which is, you know, even though I'm giving this kind of random simple example, this is even relevant today, right? So when we're thinking about what's going to happen with cafe standards, you want to look at a scenario in which, you know, Trump overturns the standards, and, you know, we may, as sort of a general public, be upset about that, particularly if you are more sort of environmentally conscious and oriented. You say, oh, that's that's bad for our environmental sustainability and our energy futures, because you're going to have low fuel efficiency cars. But if you are like a scientist or engineer or some kind of stakeholder, you want to know what's going to happen if the policy does actually get overturned, right? And we want to be able to measure those impacts. And then we can think about, oh, what would happen if all new cars were required to get like 35 mpg after 2016, or if all new cars have to get to 55 or 54.5 mpg after 2025. And so everything that we're doing here really is kind of like a simplistic version of a lot of the modeling and assumptions that go behind real world policies, like the ones that we've talked about in previous lectures. So for the low efficiency scenario where no cafe, we want to develop a model to find oil use over time. So the oil use in a particular year I is equal to the number of cars times the VMT divided by the fuel economy, right? So if I have, 1 million cars that all drive 10,000 miles per year and have 20 miles per gallon, we can calculate it with this equation. And then the number of cars in the next year, remember, it grows by 2% a year. It's just the number of cars from that year times 1.02. And then you can calculate the oil use is actually going to change linearly because our fuel efficiencies aren't changing. So it's oil use that we calculated in year I times 1.02. Starting with our initial oil use in year 0 and in 2010, which is the base year for this example, which is 8 million barrels per day. Yeah, and so we can calculate that with this equation. And so if I go ahead and plot that, I can see the change in oil consumption over time without any efficiency standards is going to look something like this out to 2040. If I were to look at a second scenario where we have 35 mpg, so all new cars after 2016 have to be 35 miles per gallon, we can develop a model to find oil use over time. So the number of cars is going to be the same equation. The oil use is going to be equal to the number of 20 mpg cars divided by 20 mpg times your VMT. But then after 2016, the number of 20 mpg cars is equal to this equation. The number of 35 mpg cars is equal to this equation. It's basically the total number minus the number of 20 mpg cars that we calculated in the last equation, and then you can calculate the oil use here. So this is going to be the 20 mpg cars divided by 20 mpg plus the number of 35 mpg cars divided by 35 mpg multiplied by the same VMT. And you can get you'll end up getting a plot like this that shows how oil consumption changes if you did implement a 35 mile per gallon target in 2016. And we can see how much oil we're saving in this case. And then the maximum efficiency scenario. So all new cars are 35 mpg after 2016, and then 54.5 mpg after 2025. It's the same type of logic here. We're using the same sort of set of equations, but we have an additional set here for 2025 and beyond, where you have 35 mpg cars, or the number of 35 mpg cars in a particular year is equal to 2024 times the same sort of equation that we use for calculating the number of 20 MPG cars, and then you just have the 54.5 MPG cars is equal to the total number of cars minus 35 MPG cars. And you can calculate the oil use here. So again, I'm not going to get into too many details about the equations. I think that if you spend a minute to look at the equations, you can see, you could figure out what's sort of going on here yourself, right? And this is driven a lot by our assumptions. It's sort of systematically structured in a way to get the outcome of interest, and we're able to measure these pretty simple scenarios of what the oil consumption is going to look like over time. And so here we can see that in the most aggressive oil use changes, that you can see a decrease even beyond what is shown in the previous scenario. And so these combinations of scenarios are very handy for understanding how implementing a particular policy will lead to a specific outcome. Okay, whoa, hang on. I think my Dropbox didn't sync. Give me 1 second. Let me quit out of this. And hopefully, okay, I think this one will have it. Jump back to the last slide. Okay. Yeah, so if you are interested in looking at more details about organizations, scientific and even regulatory organizations that have looked at future of energy and a lot of the scenarios that are generated and a lot of those resources from whom I've drawn a lot of material for this course, like basically a lot of those plots that look into the future about, adoption of a technology or energy use or emissions. Those are typically coming from organizations in this list or organizations similar to these lists that have a sort of vested interest in understanding what our energy system is going to look like, how that's going to affect climate change. And so this includes IPCC, the IEA, the International Energy Agency located in France, EASA, which is another international agency looking at energy systems. I believe they're located in Austria. PNNL develops a lot of the integrated assessment models that are being used by IPCC. That's the Pacific Northwest National Laboratory, and they do a lot of joint work with University of Maryland. And then there's the Energy Information Administration of the US Department of Energy that does lots of forecasts, both US and sometimes globally, but it's mainly US focused. They have a lot of really good resources for basically all the sectors of energy and transportation that you could think of. So future scenarios to inform policy. So again, to reiterate, why is this important? We have to first understand the future to help guide it. And that's sort of more of the sort of forecasting that I was talking about. So understanding what may happen if we're on sort of a business as usual trajectory, and then to help inform future outcomes for policies, we need to be able to provide guidance for what happens if a particular policy gets implemented, right? And actually, this happens a lot more than you might think, where regulators and legislature may come to a research institution such as a university and say, hey, I'm thinking about trying to achieve this particular outcome, or I'm thinking about passing, policy that does this, this, and this. What do you think the impacts are going to be? And so, we may be able to do some research and rapidly provide a response that says, hey, like this is what's going to happen, or we think this is what's going to happen if you choose to implement this particular policy. It can also be insight into a variety of plans. And so, maybe a policymaker or stakeholder says, hey, like we're thinking of X, Y, and Z. What do you think would happen if we did X versus Y versus Z? And we may not necessarily have a say in which policy ends up getting implemented, but we are able to provide some perspective, across different insights for a variety of these plans. Okay, so that is basically the conclusion of today's lecture and the last lecture for the class. Thanks everyone for bearing with basically a sort of newly put together class. Yeah, and I understand that this quarter has been particularly difficult, being entirely online only. I don't know what it's going to look like in the future, and yeah, it's kind of a bummer that I don't get to see you guys in person. But if you guys are still around next year, I'll be here if you want to swing by and say hi. My office is actually over in West Village, but I teach a variety of classes, mainly at the grad level. But if you ever want to find me or chat, or if you find any of the stuff particularly motivating and you want to get involved with the whole energy and transportation and climate world, definitely feel free to reach out. Happy to chat about it at any point. Yeah, and so I guess I will see you guys next week for presentations. Yeah, let me know if you have any questions. Otherwise, it's been fun teaching you, even if I haven't been able to see you. Yeah, and that'll be that for today. I'll stick around for a couple minutes for questions if anyone has anything afterwards.